So we shall start these sessions 7G. The topic of this session is nanomagnetism and spectronics. We have one invited speaker and three contribution speakers. So the first talk is an invited lecture by Dr. Matthias Oppel from Weather Messe Institute for Low Temperature Physics, Germany. The title of his talk is Spin-Hole Magnetoresistance in Antiferromagnetic Insulators. Would you start, Dr. Oppel? Okay, Dr. Oppel, could you start, please? Hmm?
I think now I managed to unmute my microphone. Can you hear me?
Yes, please. Yes.
This is great. So now I try to share the right screen, which should be this one. Screen sharing. Does it work? Can you see the screen?
Yes, yes, please.
Okay, wonderful. So sorry for the delay, and thank you very much, Mr. Chairman, for the kind introduction. I also want to share to thank the organizers of this conference for giving me the opportunity to share our latest results on the spin-Hall magnetoresistance in antiferromagnetic insulators. Of course, this work would not have been done without the help of many people. All the samples were prepared in our labs at WMI, Walter Meissner Institute in Germany, and all the magnetotransport measurements were also performed here by those people. The experiments we did with element selective X-ray techniques were done at the European Synchrotron Radiation Facility in Grenoble in France, together with those people. And the theory was provided by Gerrit Bauer and co-workers in Sendai in Japan, together with Helen Gomonai in Mainz and Akashdeep Kamra in Trondheim in Norway. So with this, I will start with antiferromagnetic spintronics. What are the advantages of antiferromagnets in spintronics? First, they offer a faster magnetization dynamics in the terahertz regime. And second, they are robust against external magnetic field perturbations because they do not have any stray fields. And this is, on the other hand side, also a problem because it makes it difficult to read out the magnetization state. We were able to show that the spin-Hall magnetoresistance effect is a possible detection scheme for the magnetization state in antiferromagnets, and this will be the topic of this talk. We were able to show that the spin-Hall magnetoresistance is sensitive to the sublattice magnetizations and that it allows to map the magnetic spin structure, for instance, in helical or chiral magnets like these copper 2 oxide selenium oxide. The problem with antiferromagnets is, does the spin-Hall magnetoresistance effect also exist there? Can we influence the antiferromagnetic sublattices by external magnetic fields and other magnetic fields magnitudes that we achieve in our labs high enough to influence these sublattice magnetizations? First of all, I want to show you the principle of the SMR effect, and it is based on an interfacial spin mixing between a ferromagnetic insulator, that was in the first experiments yttrium iron garnet, or short YIG, and a paramagnetic metal with a large spin orbit coupling. In the first experiments, this was a metallic electrode of platinum. And then, in contact of these two materials, it comes to an exchange of spin angular momentum between the magnetization in YIG and the conduction electrons in platinum. So we measured in a double layer of YIG and platinum the angle dependence of the magnetoresistance. For this, we were applying a magnetic field H, and we were rotating this magnetic field in the plane of the sample, and we saw a characteristic oscillation of the resistivity as a function of the in-plane angle. The effect size is about 1 to the 10 to the minus 3. And we found that there is a characteristic angle dependence of the resistivity, which is proportional to cosine 2 alpha. So this work was done by Matthias Althammer in his PhD thesis 9 years ago. So there is a characteristic angle dependence of the resistivity. Moreover, there is also a characteristic field dependence of the resistivity. What you see here in the upper view graph is the resistivity in absolute numbers, again as a function, no, not again, but now as a function of the magnetic field magnitude at a fixed angle. And what you see in the lower view graph is the magnetization of the whole sample measured by squid magnetometry. You see that the magnetization shows a hysteretic behavior as expected for the ferromagnetic YIG, but the resistivity also shows a hysteretic behavior which we would not easily expect from a platinum metal. The same was also seen in Japan almost at the same time in kind of the same sample, also consisting of platinum on YIG. And even more, there was a third group at that time in Baltimore in the US, who also saw the same. I will come to this in the next slide. I just want to review what we have here. We have a platinum metallic electrode on the insulating YIG. Platinum is a paramagnetic metal responsible for the resistivity. YIG is a ferromagnetic insulator responsible for the ferromagnetic hysteresis. But we also see a hysteresis in the resistivity in platinum, although platinum is not ferromagnetic. And we see this magnetic hysteresis in YIG, although YIG is not conductive. So as I told you, the very same result was also seen by a third group at that time in Baltimore. The three samples were more or less the same. They consisted of a platinum top electrode on a YIG thick film, in this case 1300 nanometers, a thin film in our case 54 nanometers, another thick film here, and on GGG substrate. And these three groups saw consistent observations. So why do we see this magnetoresistance? One of the first explanations would be that platinum just becomes magnetic or ferromagnetic on the ferromagnetic YIG due to a proximity effect. This is known as the magnetic proximity magnetoresistance. Indeed, the Baltimore group found via element-specific magnetization measurements that their platinum shows a magnetic moment of 0.054 Bohr magnetons per platinum atom at room temperature. Such a magnetic proximity effect is well known and well established for platinum, but not on ferromagnetic insulators like YIG, but on conventional ferromagnetic metals. So for instance, it is well known for platinum on nickel, where people found a magnetic moment of 0.3 Bohr magnetons per platinum at low temperatures. It is also well known for platinum on iron, where people found a magnetic moment of 0.033 Bohr magnetons per platinum at room temperature. To find a magnetic moment for platinum on the insulating YIG was something new at that time. And this called for a detailed investigation also in our samples. So we prepared a representative set of samples to investigate this magnetoresistance in non-magnetic platinum via an element-specific technique. And we took the samples to the European Synchrotron Radiation Facility in Grenoble in France. There, we were able to measure element selective, the X-ray absorption near edge spectra at the energy of the platinum edge, and we were able to measure the X-ray magnetic circular dichroism also at the platinum edge. The platinum edge, there are different platinum edges. The platinum L edges are at an energy of about 11 to 13 kilo electron volts, and for this you need hard X-rays, which can be provided by this synchrotron radiation facility. So we were interested in the X-ray absorption at the platinum edge. And then we applied a magnetic field to the samples. And then we also used the circular polarization of the incoming X-rays. And with those, one can measure or calculate the magnetic dichroism by obtaining an X-ray absorption spectra at positive magnetic field and at positive helicity minus the X-ray absorption spectra at negative magnetic field and positive helicity, or at positive magnetic field and negative helicity. So with this XMCD, you obtain some information about the magnetism of the samples. With the X-ray absorption, you obtain information about the chemistry and the valence state of the samples. So let me first start with the X-ray absorption. What you see here are measurements from 7 nanometers of platinum on a YIG layer. You see clearly an absorption edge here at an energy of 11,564 electron volts. So that means this is the absorption edge of platinum. So you see here the absorption of platinum. Moreover, you see some small structure here. This is called an X-axis wiggle, and this wiggle is something characteristic for metallic platinum, and it would be absent in platinum oxide. We investigated 3 different samples. So we have 2 more samples, one with a thinner layer of platinum, only 3 nanometers of YIG, and a thicker layer of platinum, 10 nanometers of YIG. So all these 3 spectra follow the same line. Well, except for this peak, this is a diffraction, a Bragg diffraction peak, and also that one. I marked these diffraction peaks with asterisks, and they are not important here. So all the three samples show the same X-ray absorption line. We have an even thinner layer of platinum, only 1.6 nanometers, and even this layer shows the same X-ray absorption. This was all done at room temperature. Then we analyzed the height of this, so the step height of the X-ray absorption, the so-called white line intensity, in arbitrary normalized units, and we found a value of 1.25. And these 1.25 point to the existence of metallic platinum. I took this table from a publication by Kobolov, and they showed that metallic platinum has the lowest edge height, whereas platinum oxide or even higher oxidized platinum shows a larger white line intensity. So our results are compatible with metallic platinum. And then this is a view inside the lab. You see one of my colleagues who determines the intensity of the white line just using a ruler directly on the screen. And this was a screenshot at that time. So this is the X-ray absorption. And what you see in green is now the different spectrum of two different X-ray absorptions, one with positive and one with negative helicity. And this different spectrum is the XMCD, the X-ray magnetic circular dichroism. I now want to show you the XMCD signal. This is shown here for these three samples. I multiplied the XMCD by 100, and you see that there is no structure except for noise. So in particular, you cannot see any feature here where we have the X-ray absorption edge of platinum. The same is true also for the thinner sample with the thinner platinum electrode. So to check our setup, we had a reference sample with us, which is the pink sample here. This is platinum on iron, so not on YIG, but platinum on conductive iron. You see that it shows the same X-ray absorption, but it shows a very clear XMCD signal. It is the signal does not even fit to the screen here. So this X-ray XMCD signal tells us that platinum is really magnetic on iron with a magnetic moment of 0.03 Bohr magnetons per platinum, but the platinum does not become magnetic on YIG. We were able to estimate some upper limit for the maximum magnetization of platinum, which would be compatible with our spectra. And this is below 0.003 Bohr magnetons per platinum. So the platinum on YIG is not magnetic. The platinum on iron becomes magnetic. But then the magnetic proximity magnetoresistance could not be the right explanation for our magnetoresistance that we observed. So we had to look for an alternative explanation. And this alternative is the newly developed spin-Hall magnetoresistance effect. The model is based on the absorption of spin currents, and it was first formulated by Gerrit Bauer together with his PhD student Chen and published in 2013. In the meantime, many experiments in the meantime now confirmed this theory. These are just one examples. These were the first experiments which were compatible with the theory. Experiments in platinum on YIG, platinum on magnetite, tantalum on YIG, platinum on nickel ferrite, and also platinum on cobalt ferrite. So how does the spin-Hall magnetoresistance work? We have to consider the spin-Hall effect. Heavy metals with a large spin-orbit interaction show a spin-Hall effect. One of these heavy metals is our platinum. And the spin-Hall effect leads to a separation of spins whenever I drive a charge current, JE, through the platinum metal. So the spin-up platinum electrons are deflected to the right. The spin left electrons deflected to the top. The spin down electrons deflected to the left, and the spin right electrons deflected to the bottom. And it leads to a separation of spins, and the efficiency is given by the so-called spin Hall angle, which is about 0.01 in platinum. So the spin Hall effect leads to a spin accumulation of the edges of the platinum, and this spin accumulation shows a rotational symmetry. And when we now put some magnetically ordered material, so this is the view from a front, yeah, spin left at the top, spin right at the bottom. When we now put some magnetically ordered material like YIG in contact with the platinum at the bottom, then we have an interface here. And right next to the interface is the spin polarization of the conduction electrons in platinum and the magnetization of the YIG. So in principle, there are three principally different geometries with regard to the magnetization of the YIG. The magnetization of the YIG can point to the right, it can point into the blackboard, or it can point to the top. And this relative orientation between the magnetization of the YIG and the spin polarization of the conduction electrons in platinum gives rise to interfacial spin mixing between the YIG and the platinum. So the spin mixing is an exchange of spin angular momentum between the magnetization in YIG and the conduction electron spin polarization in platinum. And what happens now and what is new is that spin flip scattering is activated whenever the spin polarization and the magnetization are not collinear. And this is the case in these two right scenarios. Here, the spin polarization is not collinear to the magnetization, whereas here on the left side, the spin polarization was collinear to the magnetization. So here there is no new effect, but here we have a transfer of spin angular momentum into the YIG. This leads to spin flip scattering and a higher resistivity. It also leads to spin transfer torque and magnon excitation. But in my talk, I do not want to talk about this. I just want to talk about the higher resistivity due to the spin flip scattering. And this higher resistivity shows or is responsible for this characteristic oscillation. So what we have here is the in-plane angle alpha. If the angle is 0 degree, then we have a higher scattering. If the angle is 90 degree, we do not have that, because we assume that the magnetization of our YIG follows the external magnetic field that we apply under this angle. So how does this look like? We apply a magnetic field H. The magnetization M follows the magnetic field H. We apply an electrical current J, and this electrical current in the platinum produces this spin polarization S at the interface. Here, S and M are perpendicular to each other. We get the maximum spin transfer torque and the maximum resistivity. If we rotate the magnetic field by 90 degrees, M and S are parallel. We have the no spin transfer torque at the interface and the minimum resistivity. And this is shown here. Maximum resistivity at 0 degrees in our coordinate system, minimum resistivity at 90 degrees. And this leads to this characteristic oscillation. So what we do is we apply the magnetic field to our sample. We pattern the sample to a Hall bar geometry and apply a electrical current. Then we rotate the magnetic field and we measure the longitudinal and the transverse voltage and resistivity. I just want to show you the longitudinal voltage and the longitudinal resistivity, and then we see this characteristic angle dependence. Now, we can also rotate the magnetic field not in plane, but we can rotate the magnetic field out of plane, perpendicular to the current direction, and we see the very same. We can apply the magnetic field out of plane perpendicular to the transverse direction, and there we see nothing. We just see a constant resistivity, because here in the magnetization is always perpendicular to the spin polarization S. So this geometry here is not sensitive to the SMR effect, but it would be sensitive to the anisotropic magnetic resistance, the AMR effect. This geometry is not sensitive to the AMR, but it is purely sensitive to the SMR effect. We fabricate our samples using pulsed laser deposition in our labs. So this is a photograph of our lab. The principle of pulsed laser deposition is well known here. We use an ultraviolet laser and hit the polycrystalline target of the material we want to deposit. There we create a plasma and we place a substrate in the plasma, and then we deposit the plasma on the bottom of this substrate. So we were growing the yttrium iron garnet. The growth parameters are given here. We were also growing antiferromagnets like nickel oxide and hematite. And the crystallographic structure is given here. And the details of the growth conditions are given here. All the work is published in these two papers by Johanna Fischer and al. We found an epitaxial oriented growth of all our samples and no secondary phases. So yttrium iron garnet is quite complicated. This is a view of the unit cell. This is not so important now. What is important with the yttrium iron garnet is that it is ferrimagnetic with a Curie temperature of 560 Kelvin. And because it is ferrimagnetic, it has two magnetic sublattices. So the iron D sublattice and the iron A sublattice, they do not compensate each other, and therefore there is a resultant net magnetization M, and this magnetization follows the external magnetic field H. And when we rotate H, we can rotate the M, and the angle between H and M is 0 degrees. So M is always parallel to the external magnetic field. This is not the case in antiferromagnets. In antiferromagnets, we have two compensating magnetic sublattices with a quasi-zero magnetization M. And due to energy considerations, these two magnetic sublattices, so for instance, the nickel 2+ sublattices in nickel oxide, they do not orient parallel to an external magnetic field, but perpendicular to an external magnetic field. That means in the antiferromagnets, the magnetic sublattices are perpendicular to the external magnetic field. The same is true for the hematite, with the small difference that we have a small canting angle between these iron sublattices in hematite with a small net magnetic moment. But also here, the magnetic sublattices point more or less perpendicular to the external magnetic field H. And when we now apply a magnetic field to a double layer structure of platinum with an antiferromagnet, we find that the magnetic sublattices are pointing perpendicular to the external magnetic field. When we rotate this magnetic field and again observe the resistivity of the platinum, we again find this oscillation, but the oscillation is shifted by 90 degrees with respect to the earlier experiments in the ferromagnets. So this was first shown in nickel oxide platinum and also in chromium oxide tantalum, and then in hematite platinum in these publications. This was theory. In our experiments, we applied magnetic fields from 1 to 17 Tesla, and we rotated the magnetic field in the field plane, and we find this oscillation now, which is proportional not longer to plus cosine to alpha, but to minus cosine to alpha, which is a shift of the oscillation by 90 degrees. We also analyzed the SMR amplitude as a function of the magnetic field, and we found that it increases quadratic in the magnetic field. We were able to explain this with the model assuming antiferromagnetic domains, but this goes beyond the scope of this talk. I want to show you the newest data from hematite, another antiferromagnet with platinum, and it shows the same oscillations, minimum at 0 degrees and maximum at 90 degrees. But we see that the SMR amplitude increases much faster and then saturates around 3 Tesla.
Excuse me, Professor, we
yes.
have 2-3 minutes more.
Thank you. So I will come to the end, and I want to compare here the ferromagnetic insulator YIG with platinum and the antiferromagnetic insulators hematite and nickel oxide with platinum. You clearly see the shift by 90 degrees. So it was 0 degrees for ferrimagnets and 90 degrees for antiferromagnets. And I can show you at the end the other two rotation planes when we rotate the magnetic field there. Then you see again in gray the well-known result from platinum and YIG. In red you see the nickel oxide. In blue you see the magnetite, sorry, the hematite. And you see that for these out-of-plane rotations, the behavior is different from the YIG. It is summarized in this table. So for the out-of-plane rotations in easy-plane antiferromagnets, we expect constant values when we rotate the magnetic field out of plane perpendicular to J and perpendicular to T. We find a high resistive state for this rotation and a low resistive state for that. And there are 3 or 4 features. These are these points. We have these cusp-like features, and these cusp-like features are always appearing when the magnetic field is perpendicular to the plane, because then we end up with the multi-domain states of the antiferromagnets. So I skipped the outlook. With this, I want to summarize. I showed you the spin Hall magnetoresistance in easy plane antiferromagnets, nickel oxide platinum and hematite platinum. I showed you that we found a resistance modulation consistent with the SMR and an oscillation which is phase shifted by 90 degrees with respect to the collinear ferromagnets. And we found a very large SMR amplitude of 2.5 times 10 to the minus 3. We developed a comprehensive model for the SMR in the multi-domain antiferromagnets. We showed the fully angular dependence in 3 orthogonal rotation planes, found a magnetic field-induced domain redistribution and a multi-domain state whenever the magnetic field is pointing out of plane. This work, of course, would not have been possible without the help of many people. I want to thank all of them. I thank the Deutsche Forschungsgemeinschaft for financial support, and I thank you for your patience and for your attention. Thank you very much.
Thank you very much. Very quite impressive talk. So now the paper is open for discussions. And we have questions from participants. Could you give questions? The participants, so give a question from chat room. Could you give your comment, questions?
Participant can raise hand if they wish to ask any question. We will unmute you. Okay, so it seems.
Please.
Yes, hello. So you mentioned shortly in the end the nickel oxide that had this behavior with the field. Is this also explained by the domain structure, so that the increasing field made the larger amplitude, because nickel oxide has this more complicated domains with the T domains and S domains and so on? This is what you meant by the field dependence?
Yeah, this is right. So what I meant with the field dependence was, I tried to find the right slide at the end. What we were able to show is that nickel oxide is an easy plane antiferromagnet, and our 111 plane, which we were investigating, is the easy plane. But in this easy plane, there is a magnetic anisotropy with the 100 degree symmetry. So that means we have 3 different domains in this easy plane of nickel oxide. And these 3 easy no, these three domains have the same domain fraction when we do not apply any magnetic field. But when we apply a magnetic field, then due to energy considerations, one of these magnetic domains becomes energetically favorable and grows, and the other two domains shrink. And this shrinking and growing of domains then leads to this oscillation also of the no, I got it. Sorry for that. Leads to the oscillation of the SMR amplitude. And the higher we take the field magnitude, so when we apply a magnetic field of 17 Tesla, then we have just one single domain and we can rotate the single domain. Therefore, we get a very high SMR amplitude. When we have lower magnetic field, we have a mixture of three domains, and therefore the magnitude of the SMR effect is lower.
Okay, so you mean you have only one T domain due to maybe strain in the film or something, because there's no shape anisotropy, but...
Right, yes.
Yeah,
yeah, you're right.
Okay, good, yeah, thank you.
Thank you. And I received a question from the one of audience, one of our participants. The question is, what is spin current? So could you explain again?
Yeah, this is a good question. Thank you for that. What is the spin current? I try to, sorry for that, find a slide again. Maybe this one. And I try to share the screen again. Sorry for that. Screen sharing like this. So can you see the screen again? Okay, so what we have is, so the spin current would be a flow of angular momentum, which is not connected with a transport of charges. So here what we have is the spin Hall effect in platinum. We have a charge current which flows from the left to the right. That means electrons or negative charges are transported from left to the right. And accompanied with that, due to the spin orbit interaction, spin Hall effect, there is a spin separation. So spin left goes to the top, spin bottom goes, spin right goes to the bottom. And this separation of spin would be a spin current, which is in a vertical direction perpendicular to the charge current. But it is not associated with a net transport of electric charges, because the number of negative charges which is going to the top is the same as the number of negative charges going to the bottom. Does this answer your question?
Thank you very much. So I received another questions. So I read the questions. Can I know what is the thickness dependence of platinum layer in measuring SMR and AMR effect?
The thickness dependence.
Yes.
This is not so easy to answer. So we have the magnetically ordered material and we have the platinum electrode. Both have thicknesses. So with regard to the platinum electrode, we find that the maximum effect we see at a platinum thickness of 3 nanometers. And we think the reason is the spin diffusion length in platinum. This is around 1.5 nanometers. 3 nanometers would then mean that the spins, the spin left go to the top and the spin right to the bottom, as I told you. And then we have a more or less perfect spin separation if we have twice the spin diffusion length. So maximum is at 3 nanometers of platinum. With regard to the thickness of the magnetically ordered insulator, we did an investigation in YIG. So we took a YIG sample, a YIG thickness of 100 nanometers, reduced it to 50, to 30, to 20. The SMR effect amplitude was still the same. Then we went down to one single monolayer of YIG, and the effect amplitude still was the same. But when we reduced the thickness further to half the unit cell, then the effect amplitude went down. So that means the effect amplitude reaches, at least in YIG, its maximum value and saturates for one whole unit cell thickness of YIG.
Thank you very much. And time is coming. So this is, next one is the last question. Is it all right? Shall we close?
Yes, sir. Carry on.
Okay. So next one is the last questions. So I read, did you check the composition YFEOX by RBS technique?
By RBS technique. No, we did not check the composition.
Okay. No. So thank you very much.
Thank you very much.
Yes, thank you again, Professor.
Professor Tasuka, please pardon me. I personally excuse. I was late to join. I'm the rapporteur. There was a little technical problem at my side. So before proceeding, I apologize everybody. And let me first introduce Professor Tasuka. Professor Hirokazu Tasuka is a professor of electronics and material science, Department of Engineering, Graduate School of Integrated Science and Technology, Suzuka University. Professor Tasuka is interested in silicon-based nanoseed bundles, growth of silver nanostructures as antiviral, antimicrobial agents. He has published several research articles in reputed journals world over and received many prestigious awards and recognitions. Let's carry on. Let me stop and we can go for the next contributory lecture.
Okay, thank you very much. So we move on to the next talk, the CL133, the study on magnetocaloric property of the SRFE MXO nanoparticles for environment-friendly magnetic refrigerations. Will be presented by Idija. Sorry, please start.
Good evening, sir.
Yes, can I hear you?
Yeah, you are audible. You can proceed.
Good evening, one and all present here. Myself, Induja, doing my research in the topic of study on magnetocaloric properties of strontium hexaferrite nanoparticles for environmental friendly magnetic refrigeration. Magnetic refrigeration is a cooling technology that works on the principle of magnetocaloric effect, and it is used to attain extremely low temperature, that is below 1 Kelvin. It is discovered in pure iron in 1881 by E. Warburg. The advantages of magnetic refrigeration is here there is no need of compressor like vapor compression technique, and there is no need for refrigerant gases like CFC and HFC gases, and this is a low pressure operation and environment friendly and highly reversible and safety cooling and inflammable and low running cost. So properties of magnetocaloric material is material should have high magnetocaloric effect, that is adiabatic temperature should be high, it should have high Curie temperature, and change in magnetic entropy value should be high, and specific heat capacity should be low, and high thermal conductivity, and the material should be non-toxic and highly resistant to corrosion, and high electrical resistance, low manufacturing cost, and low environmental impact. So this is the working principle of magnetocaloric effect. Here there are 4 steps that involves adiabatic magnetization, isomagnetic enthalpic transfer, adiabatic demagnetization, and isomagnetic entropic transfer. In the whole, here the total entropy remains constant. That is, the total entropy is the sum of magnetic entropy and the thermal entropy. This is the working principle of the magnetic refrigerator. In adiabatic magnetization, here the adiabatic magnetization happens. Here the magnetic entropy decreases and the thermal entropy increases. And here, if we remove the magnetic field, adiabatic demagnetization happens. In that, the magnetic entropy increases and the thermal entropy decreases. Once the equilibrium is obtained, the cycle repeats. I have chosen strontium hexaferrite nanoparticle, and it is a magnetoplumbite type hexagonal ferrites with a Fe12O19 structure. It is also known as hexaferrites, are the most commonly used magnetic materials because of their high chemical stability and cost efficiency. And this is the experimental procedure. My main precursor is ferric nitrate monohydrate and strontium nitrate. Both were taken in stoichiometric ratio in 12:2 ratio and separately dissolved in 20 ml of deionized water, and both the mixtures were stirred for 15 minutes. And I have undergone green synthesis. I have chosen lemon extract as a capping agent, and 15 ml of lemon extract were added. And after continuous stirring of after 20 minutes, 5 ml ammonia was added dropwise and until pH became neutral, and the temperature was increased to 150 degrees Celsius, and a brownish solution was formed. And we after constant stirring, water evaporates and becomes gel, and gel gets autoignited suddenly, and the obtained powder was washed and dried in oven at 80 degrees Celsius for 48 hours, and the obtained samples were calcined at 850 degrees Celsius for 120 minutes, and SrFe12O19 nanoparticles were obtained. This is the graphical abstract of the strontium hexaferrite nanoparticles. And this is the hexadic. I have doped cobalt and this is copper. I have chosen cobalt and copper for doping in strontium hexaferrite nanoparticles, and this is the pattern for undoped material, and this is for cobalt doped, and this is pure hexaferrite strontium nanoparticles were formed with space group of P63 per mmc, and the crystallite size of strontium hexaferrite nanoparticle was found to be 23 nanometer for undoped sample, and 17.49 nanometer for cobalt doped, and 17.51 nanometer for copper doped, and this was calculated using Debye-Scherer's formula, and all the patterns were well matched with the standard JCPDS data. And this is the SEM analysis. The structural and morphological studies were studied using SEM analysis, and the nanoparticles calcinated at 850 degrees Celsius exhibited needle-shaped morphology. And the elemental composition were studied using EDAX analysis. The spectra have verified particles without impurities and a good estimate with stoichiometric amounts of elements in nanoparticles. And this is the VSM analysis of strontium hexaferrite nanoparticle. This curve clearly shows that the coercivity of the sample strontium hexaferrite nanoparticle decreases with cobalt and copper doping. And the retentivity also decreases, and saturation magnetization also decreases. So strontium hexaferrite and Cobalt and copper-doped strontium hexaferrite nanoparticles were successfully synthesized by salt gel autocombustion method through green synthesis. The crystallite size of and cobalt and copper-doped strontium hexaferrite was calculated to be 23 nanometer, 17.49 and 17.51 nanometer using Debye-Scherrer formula. The surface morphology of the synthesized sample was examined by episome analysis. The elemental composition of the samples were analyzed using IDAX analysis, and the magnetic properties were studied using DSM analysis, which shows that the cobalt and copper doping in strontium hexaferrite nanoparticle decreases the coercivity. I think this decrease in coercivity during doping will be, it ensures that it is a promising material for magnetocaloric effect. So if the coercivity decreases, the loss will be low, and during operation, the hysteresis loss will be less, so the life cycle of the refrigerator can be increased. So further, the coercivity, decrease in coercivity should be tuned by doping, by varying the doping concentration. That has to be done. And the RCP, further, the RCP values and magnetic entropy change should be calculated in order to calculate the efficiency of the magnetic refrigeration. Thank you.
Thank you. Thank you very much for very interesting talk. Now the paper is now open for discussions. So could you, from participant, if is there any questions, could you raise your hand? Yes, please.
Yeah, I have a question. This is Dr. Ravindra. Can you hear me? Can you hear me, Mr. Vijay?
Yes, sir. Yes, sir.
Yeah. As far as I understood, you have doped cobalt and copper into your parent material to improve the magnetic caloric effect performance of your core component, right? So why have you specifically chosen cobalt and copper? Why not any other transition method?
Cobalt, nickel, and copper are ferromagnetic transition metals, sir. So they have high magnetic moments.
Cobalt, nickel, and copper.
And copper.
Copper is not ferromagnetic in nature.
Oh. Okay.
Iron, cobalt, and nickel are ferromagnetic in nature, as far as I know.
Is iron, nickel, and cobalt. Is.
That's why I don't understand. Like if you had used nickel and cobalt, I could understand that since both are ferromagnetic in nature.
Okay.
You have chosen cobalt and nickel, but you have chosen one is ferromagnetic in nature, cobalt, whereas copper is ferromagnetic in nature.
Okay, so we'll look into it. Any other questions?
Okay, is it? Okay, if no questions, so thank you again.
Thank you, sir.
Thank you.
Thank you very much. Okay, shall we move to next talk? CL134, magnetic and
Professor, you are muted yourself, I think.
Sorry.
Yeah.
So next talk is title is magnetic and magnetocaloric properties of rapidly solidificated DYL2 nanostructures. We presented by Mitalumadi Kuzmita Prusty. Could you start?
Sure. Good afternoon, everyone. This is Mitali Madhusmita Prusty, research scholar in IIT Madras. So I'll talk about today magnetism and magnetocaloric effect in meldspun nanostructured RAL2 rare earth intermetallic compounds, where R is dysprosium and erbium. So outline contains introduction, synthesis and characterization of Melspan RL2 compounds, magnetic and magnetocaloric properties, and summary. The magnetocaloric effect is the basis for an alternative refrigeration technology. It is expected to be a promising technology to replace conventional gas compression expansion technique. The operation includes heating and cooling of a magnetic material upon application or removal of magnetic field under adiabatic conditions, which will give rise to magnetic entropy change and variation of temperature. So why I have chosen RL to intermetallics? Because they show the presence of ferromagnetism and they exhibit large magnetocaloric effect near their Curie temperature. From the figure, we can show that see that GDL to intermetallics, they are showing a broad transition near Curie temperature. And also for DYL2 sample, it is showing a broad transition near TC, which is a good property to be a good magnetocaloric material. Now, the rare earth-based nanoparticles has so many applications like high-density magnetic storage, high-performance permanent magnets, and magnetic refrigerants. So the nanoscale lanthanides, their alloys and their intermetallics are of current interest due to their novel magnetic properties. Now we'll talk about characterization and results of my samples. I have chosen arc melted DYL2, Melspan DYL2, arc melted ERL2, and Melspan ERL2. So from this powder X-ray diffraction data, we can see that these samples are polycrystalline, cubic Lewis phase MgCu2 type structure having space group FD3 by M. I have calculated the crystallite size using Scherer formula, and it is about 33 nanometer for Melspan DYL2 sample, and it is about 31 nanometer for Melspan ERL2 sample. Then from this transmission electron microscopy results, I have calculated the average particle size, which is about 32 nanometer for Melspan DYL2 sample, and it is about 26 nanometer for Melspan ERL2 sample. And talking about magnetic properties, here is the transition. We can see the transition temperature of all four of the samples. The zero field cooling and the field cool warming plot merge with each other for 5 kilo field for all of the samples. And from here, we can see the transition from paramagnetic state to ferromagnetic state. I have listed the Curie temperature, paramagnetic Curie temperature, and effective magnetic moment of some of my samples and a few other samples. Here we can see the Curie temperature has been reduced for Melspan samples. This is 29 from 61 from their from both of the samples from their arc melted counterparts. So we can see that this is the proof of formation of nano grains. So which has reduced the Curie temperature. And here we can see the magnetization versus field at 5 Kelvin, and it is for 2 Kelvin. Here we see that there is a negligible coercivity, which proves that these are soft ferromagnet. And I have listed the magnetization at 70 kilo field for these samples. And here I have plotted magnetization versus field for different temperature ranges using this thermodynamic Maxwell equation. And from this, I have plotted this negative of change of magnetic entropy versus temperature plot. Here you can see that for arc melted DYL2 sample and arc melted ERL2 samples, the transition is sharp at TC and have high value of the negative of delta SM. But for Melspan DYL2 sample, the transition near TC is broad, and this broad transition is a good is good to be a good magnetocaloric material. And here I have listed the peak temperature where this the negative of delta SM is maximum, the Curie temperature and the negative of maximum of change of magnetic entropy for different field values, and the relative cooling power of some of the samples. And this shows the dependence of change of magnetic entropy upon the change in magnetic field. And I have calculated the N values for these 4 samples. And so in the summary part, I have listed the Curie temperature, peak temperature, and the negative of maximum of delta SM and RCP values for 4 of my samples. And here you can see that the Melspan DYL2 and Melspan ERL2 sample, the RCP has been reduced. Also the Curie temperature, which shows the formation of nano grains. Thank you.
Thank you very much. Very interesting talk. Now paper is open for discussions. So if Yeah. There any questions and comments from participants? Please raise your hand. Can I, if no, can I give one questions?
Sure.
Okay, so using these materials,
Yeah.
is it possible to improve the property?
I'll try by doing annealing, and like if you can see the table, the RCP is nearly equal, but okay, I'll try by annealing or anything if we can improve the RCP.
So do you have any idea to improve it?
Yeah, I think I will do annealing or something to increase the RCP values.
Okay. Okay. Okay, please.
Is that the RCP values or these, I mean, the property does depend on size of the particle, or is it?
Yeah, property depend on size of the particle. Because the TC will change then according to the size, and the broadening also will differ in this peak. If the size will decrease, then the TC will be maximum for different size distribution of the particles, and the broadening will be there. So broadening also, for good magnetocaloric material, we need maximum of negative of delta SM, also the width full width half maximum.
Smaller is the particle, better it is, right?
Yeah.
Okay. Thank you.
Thank you.
Okay, please. Next question, please. Dr. Reddy from Canada. Could you give questions? More. Okay, so just I read the sentence, but it's just shown. Chat window shows just a part of questions. But if I read, the question is for XRD spectra.
Yeah.
So yeah, so lines is it sharper? It maybe so. I'm not understand this question because just question shows just a part of the sentence. So why more sharper? More crystallines. Yes, why more sharper? More crystallines.
Pardon me.
The question is why more sharper and means that more crystallized. That's what you said, I guess. Is the question from MB ready? I'm just unmuting, or she can ask this.
Okay, because
you can. Yeah.
I'm Dr. Reddy. In fact, previously also have some questions. In fact, you need to unmute. It is okay. So regarding for the small comments for the students, especially in XRD, maybe make sure that don't put intensity in atomic units. By seeing the spectra, it looks like more sharper.
Yeah.
So in people, don't use that Scherer equation, because usually high temperature sample, like telling nanometer is not really correct. Make sure that what is the shape of the particle. So that's why sometimes we may not get expected nanocrystalline nature, you know. Okay, check that one, okay?
Sir, actually, I can't understand. Like you are telling not to use this Scherer formula.
No. It depends on the particle size. Your particle size below spherical, and then some limit. You know, if it is the micron size particle, if you use the Scherer equation, it will be correct. And also, if particle, if it is rod, and then I don't know how the particle look like. You have to check that one also.
Yeah, actually, my samples are also like I can't say these are exactly nanospheres.
Yeah. That's why you have to be careful. So we cannot, if it is spherical, and then you have to see. Okay. Anyway, overall, by checking your pattern, it looks like I can tell that the submicron size material. So okay. Yeah, overall okay. So sometimes, you know, nowadays
Okay.
people will do. So try to check that one. Correct that one. Okay.
Okay.
Yeah, good luck.
Thank you.
Okay. Thank
Okay,
you.
thank you very much. Maybe the last question is, I read, what is a change in isothermal temperatures? So maybe if you change temperatures, maybe what happens?
Sir, can you repeat again? I can't understand.
So I read, what is a change in isothermal temperatures?
Isothermal temperatures.
Yes. If you
Okay.
change, what happen?
This one.
Maybe.
No, maybe not this one. The isothermal temperature. Temperature based data that you had shown.
Temperature.
Yes.
Okay. 1 minute. So this TC you are asking about?
Oh, okay. Thank you.
Please. Carry on, please.
Yeah, you please carry on.
Hello.
Could you explain?
Like if you see, this is my work. This arc melted divided to this TC is 61, but melt span divided to it has been decreased so much, like 29. And this ERL to case also TC has been reduced because in melt spinning process, the nanograins formation is there. That's why the TC is reducing.
Okay, thank you very much. Now, time is up. So thank you again.
Thank you.
Thank you so much.
Thank you very much. So we move on to the last presentations. The title is Post-Treatment Studies on FECO NIO Exchange Biased Thin Films. Will be presented by Sangees. Please start.
Sangeet, you are not audible. If
hello, am I audible? Hello.
Yeah. Now carry on.
Okay. Presentation. Sorry, is it visible? Hello.
Yes, it is. Please carry on.
Yeah. Hi, sir. Good afternoon, everyone. Myself, Sangeet K from School of Instrumentation, Devi Vishwavidyalaya, Indore, India. Today, I'm going to talk about the post-treatment studies on FECO and NIO exchange bias and thin film. So today, my outline contains introduction of the exchange bias, thin film profiling by X-ray reflectivity, X-ray diffraction using image plates is done in the beam RR-cut beamline, and car microscopy studies and squid microtometer studies of the NIO FECO by there. So while going to the introduction, NIO and FECO, we have chosen nickel oxide because it has a high nil temperature, which is allows ones to application under the room temperature, and the FECO has a high saturation magnetization among the 3D transition metal, which we use as a ferromagnetic metal. So while going to the device application, spintronic devices, the stability and high density are the most important. So just go for the exchange bias. Exchange bias is the phenomena that occur in antiferrometric ferrometric system as one field cool the system below the nil temperature. As one seen that from figure A, the antiferromagnetic ordering will be disordered in state above the nil temperature. As one coming to the below the nil temperature, the antiferromagnetic order will came into the picture, and the antiferromagnetic spin just antiferromagnetic spin just below the ferromagnetic will align ferromagnetically, and when reversing the magnetization, extra force required to reverse the magnetization. This will leads to the shift in the hysteresis loop. So what the work we have done, we have used the ion beam sputtering to deposit the nickel oxide, and on top of that we have deposit the FeCO, and nickel oxide we have deposit in the presence of oxygen partial pressure. So the modification we have done by using the swift heavy ion radiation from the IUH in New Delhi Center. There we can change the interface. There we can change the interface by the swift heavy ion radiation. Also the structural characterization also we can structural properties also we can change by the swift heavy ion radiation. Here we have used swift heavy ion which is dominated by the electronic energy loss. And the characterization mainly we have looked the XRD, XRR, and skewed and curve microscopy we performed on these samples. So while going to the result, as one we can see that after the irradiation, the interface roughness has been developed after the irradiation, which means that the pinning centers has been enhanced or developed in this particular system. This pinning the roughness enhancement in the interface will be contribute to the coercivity enhancement, which will be discussed in the magnetic studies. Not for the structural characterization, we have performed image 2D image plate using RR facility, and we have see that the stress induced in the stress induced during the deposition has been relaxed after the irradiation. The peak of the peak corresponding to the FeCO and NiO has been shifted to lower angle sides, which means that the stress induced during the deposition has been relaxed after the irradiation. So while going to the magnetic studies, we have used we have field cooled the system from 550 Kelvin to room temperature to understand the exchange bias. From figure we can see that the coercivity of the particle film has been enhanced, which means that due to the pinning centers present in the interface is enhanced the coercivity. But here we can see that the exchange bias has been reduced. That means that we not normal in this case. But to understand more about the exchange bias here, we again field cool the system from room temperature to low temperature, that's 5 Kelvin. That we can see that the exchange bias and the coercivity both are enhanced. This means that at the interface, the frozen spin presence in the interface may contribute to the enhancement of the exchange bias. Moreover, the magnetic studies, the current domains are present in the initial state, that's without the radiation, and those are nucleated in the pristine stage. After the irradiation, then domain wall motion has appeared. More of the training effect, that is repeated cycling of the hysteresis loop will be reduce the coercivity and the coercivity and exchange bias. So here we can here the training effects will be absent. This means that there is a simulation called Hofmann's simulation. From here he has explained that the presence of the uniaxial anisotropy present in the antiferromagnetic will be contribute to the absence of the training effect. So if the Hofmann said that if the symmetry present in the antiferromagnetic will be biaxial, it will be shows the training effect, and in the case of the uniaxial, it will be the absence of the training effect. So in conclusion, we have deposited the NIOPCO system, and it shows the exchange bias and exchange bias at lower temperature. The NI radiation has enhanced the coercivity and exchange bias at lower temperature. The stability of the exchange bias were found to be higher compared to the other system. That is, and stability parameters is correlated to uniaxial anisotropy present in the system. Thank you.
Thank you very much. Very interesting talk. Now the paper is open for discussions from participants. So if you have any question, comments, please. Any questions?
You can raise hand. We will unmute you if anybody is there.
So if no, can I give questions?
Yes.
Okay. So by post-treatment, so which characteristic is improved and which one is degraded? Okay, just simply, yes, please.
So actually, the stress induced in this film has been reduced, but stress relaxation has been appeared. That's evidenced by from the XRD pattern, and also the interface that we can see. That interface has been enhanced, developed. The interface is modified. That's it's become more rough surface after the radiation. So this what will happen is when we this roughness will increase, the pinning center at the interface will be create more exchange bias.
So what is the epitaxial? Is it epitaxial films? And
no, it's a polycrystal films.
Polycrystalline. Is there any specific reason that you use only polycrystalline? Because most of the studies, if you noted in the bilayer or multilayer magnetic films, they are generally epitaxial.
Yeah, means I have, but here also in polycrystalline studies also we there exchange bias means my topic is related to exchange bias. So in polycrystals also there are many reports are there. Yeah, in epitaxials also there are.
What is the thickness of the film?
Sir, it's actually nickel oxide is 80 nanometer and FPCA is a 30 nanometer.
So there is a question, I guess, in the chat. How could you calculate the exchange bias from Mr. Saratwara?
No, exchange bias we can calculate from the Fisher's slope after the field cooling. So the formula will be the HC and HC is the calculation formula. HC1 and HC2 are the cohesive field near to zero magnetization.
So that basically represents the exchange bias.
Yeah.
I hope
that shift in the Fisher's slope basically represents the exchange bias. How much it shift along the field axis.
Okay. Any other questions?
I think
so if no, okay. Okay. Thank you very much. Thank you.
Thank you everybody for joining the session, and thank you Professor Tasuka from chairing the session. It was wonderful. Thank you again, all from the ICONN team.
Well, thank you. So thank you again for all speakers and participants. Thank you. Yeah. Okay.
And just an announcement before anybody, you can join the keynote lecture after this. Yeah, it's already started. Thank you, everybody. All can join the keynote lecture if using the other link. Thank you.